Humanity has mastered the art of looking up. We've sent the Voyager 1 probe punching through the edge of our solar system, sailing over 15 billion miles into the dark. But if you ask us to look down, to physically bore into the rock beneath our feet, our reach is strikingly short. This cross-section shows the true scale of the Earth's interior. The center of the core sits roughly 4,000 miles below the surface, yet we live entirely on a paper-thin outer crust that we've barely managed to scratch. The limit of human excavation sits under this rubble in Russia. In 1970, the Soviet Union launched the Kola Super Deep Borehole project to see how far down they could drill. After 2 decades of grinding through the crust, they stopped at 12.2 kilometers. That is roughly 7.5 miles down, just 0.2% of the distance to the center. Even today, modern efforts hit a similar ceiling. China recently launched its own scientific drilling project, but the target depth is still limited to 15 kilometers. From a structural and financial standpoint, it is easier to land a billion-dollar robotic rover on the surface of Mars than it is to dig 10 miles straight down into our own planet. The Earth actively fights back. Once you push past 12 kilometers, the subterranean environment turns hostile. Temperatures spike to 180 degrees Celsius, and overhead crust creates massive pressure. The problem isn't simply that metal drill bits melt. Drilling stops because you hit a boundary geologists call the depth wall, where the physical behavior of matter changes. This is rock plasticity. Under extreme heat and pressure, stone stops acting like a brittle solid and starts acting like a fluid. Maintaining an open borehole becomes physically impossible. The moment a drill bit is withdrawn, the surrounding rock flows inward to seal the hole. This creeping rock traps pipes and crushes mechanical drilling equipment, destroying standard drill bits as the Earth squeezes the borehole shut. Mechanical drilling reaches its limit at the plasticity wall. To go deeper, we have to move beyond the concept of spinning metal blades. One proposed solution for the deep crust is millimeter wave drilling. By using high-frequency electromagnetic waves to literally vaporize the bedrock, engineers could bypass the mechanical stress that destroys traditional bits. But reaching the actual core requires something even more radical. In 2003, Caltech scientist David Stevenson proposed a method to reach the center of the Earth in a single week. The first step is to use a massive underground nuclear explosion to intentionally crack the Earth's crust downward. Step 2 requires pouring 100,000 tons of liquid iron, roughly a week's worth of global foundry production, into the crack. The weight of the iron would force the crack to propagate toward the center. A grapefruit-sized probe would ride this sinking mass, transmitting data back to the surface via seismic vibrations. A core probe mission would cost between $10 and $50 billion, placing it in the same financial category as our most ambitious space exploration programs. While a multi-billion-dollar iron probe sounds like science fiction, the data sitting at the center of the Earth is the only way to answer questions regarding our planet's ultimate stability. Why spend tens of billions of dollars just to look at hot rocks? Reaching the 10 to 15 kilometer mark makes it possible to harness super hot rock geothermal energy. Each well tapped at this depth produces 10 times the power of today's geothermal projects. This creates a carbon-neutral, base-load power source that becomes cheaper than any available alternative. But the mystery that requires reaching the actual core involves the Earth's magnetic shield. The geodynamo's liquid iron creates the magnetic shield, deflecting lethal solar radiation. But lab data suggests the core is cooling faster than models allow. If the geodynamo stops, solar winds will strip away our atmosphere, turning Earth into a barren wasteland. A direct probe is the only way to physically measure the core's thermal conductivity. It would allow us to determine how long our magnetic shield will remain intact. The quest to reach the Earth's core is a search for ground truth. It is the only way to physically model the internal engine that powers our civilization and maintains the magnetic shield protecting life on the surface.